Hi, we are the mini drone group, and throughout these slides, we'll be discussing our process as a team. Here we have our two technical directors, Dr. Paolo Stagagno and Dr. Juan. My name is Nicholas DeLuiso, and I am a senior electrical engineer.
My name is Jacob St. Germain, and I am a senior in electrical engineering too.
My name is Heather Rojas, and I'm a senior computer engineer.
The ICRL is an interdepartmental research group that heavily focuses on aerial robotics, industrial automation, soft robotics, human-robot interaction, multi-robot systems, and robotic swarms. Go next.
Our project motivation is that robotic swarms have the potential of widespread application. There's a lot that you can possibly do with this. The IC Robots Lab already has a ground robotics swarm, and they would like to expand to there. And the lab is too small for the drones that they have right now. And so in order to conduct further research, they wanted smaller drones. The anticipated best outcome for this project was a fully functional prototype of a single MAV that can be replicated to create a swarm with a max weight of about 6.6 kilograms, max size about 30 centimeters, max flight time of 10 minutes or more. It had to be compatible with ROS through an onboard computer, and it had to orient using lab equipment, the OptiTrack system that we have, and it needed a downward facing camera.
Our current project status. Currently, we have not achieved our ABO, but will continue to work until the end to overcome our current issues. We were able to construct 2 mini drones, connect our flight control units and our single board computers, and ensure they were communicating through a USB TTY connection. In addition, we were able to link the flight controller unit and the SBC to the external motion tracking system, OptiTrack. We were also able to send the OptiTrack data using a ROS topic and relaying the topic to a MavROS node, which in turn used MavLink to send the information to the flight controller unit. We were able to arm our drone, but have had trouble overcoming a software issue with takeoff commands. A summary of our key team accomplishments includes we selected and ordered all critical hardware components, assembled all drone components, soldered and wired the FTDI TTY USB adapter for communication between our flight controller unit and our companion computer, set up an onboard companion computer, completed a flight test in the lab, purchased and installed additional safety components, attached OptiTrack motion trackers and configured our drone's rigid body using the OptiTrack system, subscribed to OptiTrack pose data through ROS topic and relayed to a MavROS topic, used MavROS and MavProxy to communicate, be able to change the modes and arm our drone through terminal commands, and we're attempting to use the fake GPS plugin to take off using local pose info from OptiTrack. The economic impact of our project included creating additional graduate and undergraduate research opportunities, increase the scope of research that can be completed in the lab, and increase funding and grant opportunities for the program. This is a high-level project architecture. You can see here you have our drone with its OptiTrack motion trackers attached, flying in our motion capture cage. Our flight controller unit was the Pixhawk 4 Mini. Our OptiTrack server took our pose data and reported it back to the drone. We had a ROS master running, which subscribed to the OptiTrack data using the VRPN client node, specifically Mini Drone 1, which was our rigid body name. And here you can see that we also had a ground station computer that could SSH into the master and send terminal commands. Software research. Part of this project included learning ROS, learning the PX4 and Arduino Pilot open source autopilots, using Q ground control software for flashing our firmware and making changes, learning MavROS, learning MavLink and MavProxy, and learning how they all work together. Software integration, which was the hardest part, was getting all of these to work together. So we did have to research and implement the ROS, MavProxy, MavLink communication, implement changes to the firmware for our specific drone to allow offboard control, especially using the fake GPS plugin to allow OptiTrack pose data to be used to fly the drone by velocity commands. And we needed to create documentation for the project. We also had to calibrate OptiTrack. Here you can see our Mini Drone 1 rigid body. We calibrated the OptiTrack cage using the wanding technique, attached 4 motion trackers to our drone in strategic locations for the best results, created the Mini Drone 1 rigid body, and we changed the default coordinates to stream up as Z where the default is Y. The fake GPS and troubleshooting was also of high difficulty. We did attempt to pass OptiTrack pose data through remapping topics from BROS to MABROS, which was successful. We also attempted to use the fake GPS plugin and set parameters to allow the mocap data to be used as GPS data to enable the drone to know its location in the cage. We also confirmed the flight controller unit did receive pose data and could arm, but was denying our takeoff requests. Checking the error logs didn't seem to provide a root cause for the issue, and we did spend quite a lot of time troubleshooting. Up next, I want to introduce one of our electrical engineers on our project, Jake.
Here's just another picture of our high-level project architecture again. I know Heather already went over this. But choosing hardware. Choosing hardware was one of the first steps to completing our project. It was extremely important that we chose the correct parts for our capstone, as we needed to get the right dimensions, the right weight. We needed to make sure that everything was correct. For example, the ESCs, those were a major part of the actual drone, the electronic speed controllers. The frame was another big part. We needed a lightweight frame that was durable. The battery was very important since we needed to get a flight time of at least 10 minutes, so we needed a strong enough battery to maintain all the electronics, but at the same time, we needed to ensure that the weight wasn't too large. The motors themselves were very important too, because that was the point of the drone where it will give us the thrust. And so in order to get the correct thrust was very essential for our project. The SBC, the single board computer, where we would be running ROS through. The flight controller, which would manage the ESCs and the motors. The power management board to, of course, allow the power to go to the motors through the ESCs. And the camera. There are many requirements for our choices, and we had to take into account many variables for said drone. Motor propeller ESC. So the propeller diameter was chosen after the frame size was picked. There was a nice website online where we were able to get the correct propeller size. The motor stator size was chosen based off the prop size. Choosing a motor, we needed to choose a motor that would give enough thrust to fly, but not too fast. Although we could have gotten motors that would run faster, we figured the faster it went, the more power that it would draw. So we need to find that golden time where it was enough to get the drone off the ground and allow the drone to fly, but at the same time we didn't need too strong of motors. ESCs were chosen through finding the max current draw of the motors. We didn't want to go too large past the current draw of the motors because that would decrease the efficiency. And we didn't want to have ESCs below the max current draw of the motors, or else we could burn the ESCs out and therefore make it so that the drone wouldn't be able to fly. The Odroid C4 was our SBC, our single board computer that we ended up choosing. It was able to host a Linux OS. It was very lightweight for its size and its power. It houses a heatsink on it for thermal dispersion, which is very important because as we found out throughout the project, it actually did get very hot. The lowest power draw when compared to the other SBCs we looked into, which is very important because again, we were looking for our optimal flight time. So further research, we did build the second drone too, just the same as the first drone, where we were both able to get the SBC and the FC to work with everything. We were trying to implement the camera to the system, but we ran into a few errors, a few problems. Completing the software integration was definitely the hardest part of this project, and we almost were there, but we ran out of time. And connecting the drone to either the GPS or the OptiTrack system. And up next, Nicholas DeLuiso.
Once again, we have the high-level project architecture. You can go next, please. This is the chosen LiPo battery. It is a 3-cell 1800 milliamp per hour battery with a 30C discharge rate. The reason this size battery was chosen was to optimize the drone's flight time and to ensure that the battery does not drain too quickly. The battery's connector is a male EC3 connector and is an average size weight and size. The power management board, it's very small and lightweight. It distributes power to the ESCs, motors, SBC, and flight controller. And its connector is the XT60, which we ran into a problem with this that I'll talk about on the next slide. Can you go back? It's okay. I was just gonna say that the power management board it came with the flight controller, so we didn't really have to worry too much about purchasing it. Here's the battery adapter we had to purchase. One side connected to the battery, one connected to the power management board, and the last one connected to the Odroid C4. It is a EC3 female splitter. The battery has an EC3 connector and the PMB has the XT60, so we had to cut off the end of the connector going into the battery and solder on an EC3 connection, and that solved our problem. Go next, please. The flight controller that we chose is the Pixhawk 4 Mini. We went with Pixhawk 4 because it's extremely lightweight and small. And throughout the project, we bounced around using these two firmwares, ArduPilot and PX4. They both are extremely user-friendly, but in the end, we mainly worked with ArduPilot. Finally, the Pixhawk 4 Mini came with a GPS module, and this came in handy towards the end of the project because we were able to do multiple flight attempts outside. Go next, please. This is the FTDI adapter. It's a USB to serial. You can see the labeled pins right there, and it supports 3.3 to 5 volts. It connects from the Pixhawk Mini serial port to the ground station computer. And for our key acknowledgements, we would like to thank our technical directors for sponsoring the project and always lending a helping hand. And we would like to thank Dr. Sunak for organizing and facilitating such an incredible program. Thank you very much.
Thank you.
Thank you.